about tonight's talk. So Lisa Thompson, who's a research geologist for us at the Arizona Geological Survey, is going to be giving the talk this evening. She started with us almost 5 years ago, right? It's in November of 2020, in the midst of the pandemic and everything else. So, but anyway, she's done great. We were very fortunate to get her away from NAU, and she's been involved in a bunch of different projects for us and has done a great job in all of them. But this particular project that she's going to be talking about, something that came out of it, was our first. So we did a bunch of mapping for the state map program in Big Sandy Valley, and we had a field trip a couple of years ago that some of you went on probably, showcasing the mapping that we'd done. And at the same time we had the state map projects going on in Big Sandy at the very southeastern end of, and towards Burrow Creek, we had an Earth MRI, which stands for Mapping Resources Initiative. It's a USGS program that started 5 years ago or something like that. So this is our first project in the Earth MRI program, which is focused primarily on, it's focused on mineral resources, but it's focused primarily on critical minerals. So it's very neat that we knew that in southern Big Sandy Valley there were some deposits that were fairly rich in lithium, and so this Earth MRI project involved mapping and studying those deposits, and Lisa took the lead in the project, did a lot of mapping, and worked with an industry partner, Bradda, to develop the story that she's going to talk about today, which is the basin volcano-sedimentary lithium deposit, Kaiser Spring volcanic field, northwestern Arizona. So.
Thank you. Thanks, Phil. I have a lapel, so I don't need that. Well, yeah, thanks for inviting me, Phil. This is really a privilege and an honor to come and speak to you tonight about the basin volcano-sedimentary deposit. Phil gave a nice introduction to the Earth MRI program, which I'll actually talk about in a second. But the picture that you're looking at is a picture taken across basin at one of the more prominent high-silica rhyolite domes in the background, and it's perched there on top of Proterozoic rock. And in the foreground is part of the basin sedimentary package that I'm going to be talking about today, which hosts lithium. So just a brief outline. I wanted to introduce the basin analysis research team at AZGS and what we do and why I was involved in this project to begin with. We'll get into the actual geology of volcano-sedimentary lithium deposits, because I don't think that many people are familiar with them. They're quite a new area of exploration in lithium. The regional geologic setting for basin, a bunch of really fabulous photos of rocks in the basin area. The stratigraphy and the mapping that we did out there, and some notes on the lithium mineralization, of course, which I think many people are interested in this room. So, all right, our team, who Tanya and Brian are here. I'm part of the basin analysis research team at AZGS. Much of what we do is subsurface exploration for trying to solve problems with the energy transition. So a lot of our projects involve CO2 storage in the deep subsurface and stacked saline aquifers. We have a mineralization project where we're trying to maximize mineralizing carbon dioxide in basaltic rocks and scoria. We're involved with a direct air capture hub at ASU. And we just recently put in 2 proposals for understanding the feasibility of geothermal energy in the state. We do a little bit of work in gas storage, hydrogen subsurface storage, and bedded salts throughout the basin and range. And then there's this project, which sort of fits, but not really. It's a critical mineral project, but it fits well with me because my background is in physical volcanology, and particularly in water-lava interactions, and how magmas erupt when they encounter water, both in groundwater, in surface water, and in marine environments as well. So that's how I got involved with this project and the geologic mapping in the area, because the area is abundant with volcano-sedimentary type deposits. It's not your typical lithium crystalline rock deposit. And just a note, like Phil had mentioned on the Earth MRI resources program, I thought you might want to know a little bit more about where this funding came from. We did 1 to 24,000 mapping as part of Earth MRI, the Earth Mapping Resources Initiative. And this was started in 2017 with an executive order to ensure a secure, reliable, domestic critical mineral supply. That launched the Earth MRI program in 2018, and in 2021, more money was given to that program to find critical mineral resources and understand their sort of source to sink geology throughout the United States. And that's what this work is a part of. We did 1 to 24,000 scale mapping in the basin area and surrounding Kaiser Spring volcanic field to better understand the sources of the lithium and the sinks of the lithium there, particularly when it comes to sedimentary rocks. And I would just say that this program and federal funding in particular for science is really important for developing workforce and for just influencing innovation in this space. Okay, so basin. This figure on the left is from a very recent paper from Tom Benson, Lithium Americas in 2025. So it's showing all of the lithium deposits in the world, and they are categorized by pegmatite in the red squares, closed basin brines in the blue dots, and then volcano-sedimentary lithium deposits in the yellow squares. And so what you might see, let me try this fancy pointer, is that basin in the southwestern United States is among many volcano-sedimentary deposits that have been identified there. There aren't many around the world. It's quite a new area of exploration, probably in the last 7 years or so, that these deposits have been understood. If we zoom in down the lower left-hand corner, basin is in sort of the central northwest part of the state, in the Basin Range in the transition zone. Let's see, we're not going to deal with C or D. On the right-hand side is the grade and tonnage of the basin deposit, and in compared to your traditional pegmatites and brines, and basin kind of sits right there in the middle of those. The current estimate indicated, inferred, and measured mineral resource, 641 million metric tons of mineralized rock with grades of 823 parts per million. So that's where this sits as a resource. All right, this is all right, so unlike traditional lithium deposits, you need this kind of special recipe for lithium to be concentrated in the sedimentary rock at the level of concentration in which it becomes ore. We have a lithium source, which is going to be rhyolitic magma or igneous rock somewhere nearby. It doesn't need to be right there, but somewhere nearby and within the drainage basin. We have a lithium transport either by groundwater or through hydrothermal circulation, and then a lithium trap, which is, because lithium is such a mobile element, it needs to be trapped in a hydrologically closed basin. The water needs to go in, but not come out. And this recipe then results in a volcano-sedimentary deposit, which generally is described as a stack of sedimentary rocks that are interbedded sometimes with tuffs, or not typically actually lavas, but rhyolitic tuffs, lapilli tuffs, and ash tuffs. And the sedimentary rocks that are mineralized are composed of phyllosilicates, either smectite or illite generally, and much more diverse types of really special species of clay minerals we don't really need to discuss. These deposits are also typically associated with borosilicate and phosphate ores as well. So that's the recipe. There are a number of different environments where this occurs. The only other volcanic edifice where there is an identified volcano-sedimentary lithium deposit is McDermott caldera. It's part of the Yellowstone hotspot caldera system. It sits on the border of Nevada and Oregon. And this is currently the largest lithium deposit in the United States in McDermott caldera. And the upper diagram, number 1, is showing kind of a schematic diagram of what that looks like. You have an ash flow tuff that would be lithium rich. It sits in the caldera itself. And above that are lake sediments that take up the lithium that it is mobilized by both groundwater and hydrothermal circulation. That's the model at McDermott Caldera. A second model is in extensional basins. So this figure is from another recent paper, Darren et al., 2025, who did a lot of work in Rhyolite Ridge area in Nevada. And what you're looking at are 3 extensional basins across the area of Rhyolite Ridge that all are mineralized to different grades of lithium, and they're all a result of high-angle normal faulting, creating hydrologically closed basins. There's lithium that gets mobilized from Rhyolite Ridge in pink, or maybe the tuffs that are at the bottom of the basin. There may be some hydrothermal circulation that's still up to debate, and all of that lithium gets concentrated in the smectite clays that are deposited from the lake water. So that's the model. Basin, where we are, the place I'm talking about today, is a whole different game. So this is now probably the only other volcano-sedimentary deposit recognized within a volcanic crater. And the takeaway from this entire talk is that I'm really convinced that this crater is a Mar crater that is filled with clays and tuffs. And I just wanted to review the creation of Mar craters because it's not the type of volcano a lot of people think of all the time. On the left-hand side, you have mafic magma that's rising through the shallow crust in a dike that intercepts groundwater or surface water. And that intersection of the hot magma with cool groundwater starts explosive eruptions that excavate a crater. And so the second and third diagrams here are excavation of a crater and a root zone that will continue as the water table gets drawn down. That crater, once the eruption is complete, that volcano will never erupt again. It's a monogenetic volcano. It doesn't have periodic eruptions like scoria cones. It's essentially the water version of a scoria cone. Rather than building up a cone, it excavates a crater. And what's left over is a very deep root zone that's filled with breccia. Overlying that often gets filled with water. Now we have lake sediments in that Mar crater, and you may or may not have a tuff ring around the outside. So that's one of the takeaways from this talk. I hope that I'll convince you that this is a Mar crater. That's what we wrote in our paper. But of course, we're still up to debate because Joey Wilkins at Bradda hasn't drilled to the bottom of basin yet. So we need to still see what's down there. Okay, so the regional geologic setting, this picture is actually a drone photo overlooking most of the basin sedimentary deposit. There's a volcaniclastic fan in the background up here, and in the central part, some of the mineralized clays with volcaniclastic sandstones and conglomerates overlying it. And there's a really prominent basalt flow that runs right along the text there. The rocks in this area are quite interesting. Let's see. This geologic map is oriented in a funky way. It's north is down and to the right. So you're gonna have to twist your brain a little bit. This is the area of Big Sandy Valley. And basin is located in the southeastern Kaiser Spring volcanic field. You guys probably better know it as Burrow Creek. It's a place where a lot of people go to collect agates. There's really some excellent camping there. Burrow Creek, a perennial stream that runs right through the field area. Basin is one of 3 volcano-sedimentary lithium deposits located within 70 kilometers of one another. The other is in Big Sandy Valley, which is also being explored. Big Sandy Valley is an extensional basin, so it is one of those, one of the many extensional basins that have the lithium mineralization. There's a third, Thompson Valley, which much less is known about. No relation, has nothing to do with me, I didn't name it. Also called the Lyles Clay Deposit. And then there's another sediment-hosted ore that is an old uranium mine. So this whole area is really geologically interesting. Phil mentioned, the AZGS geologists have been mapping Big Sandy Valley for quite a while. We extended that mapping into the Kaiser Spring volcanic field. In the rest of the talk, we're just going to be right here in the southeastern Kaiser Spring volcanic field. I also should mention that Baghdad is a very conspicuous copper porphyry mine, just about 13 kilometers to the southeast of the basin deposit. Okay, this is a simplified geologic map. I want to start, let's see, this is the Kaiser Spring volcanic field. It is a bimodal volcanic field, so it has both basaltic and rhyolitic eruptions. The silica gap there is about from 57 to 69 weight%. So there are no rocks in the middle of that gap in terms of silica. The eruptions in this field started 15 million years ago or so with tholeiitic basaltic lavas, and that quickly transitioned to alkaline. And those lavas are interbedded with all of the rhyolites and all of the tuffs. So the basaltic eruptions were intermittent. And during the same time, we had high silica rhyolite domes erupt starting around 12 million years, transitioning to low silica rhyolite domes later around 8 million years or so. We don't have very good time constraints on these domes. But the left-hand map is showing the Kaiser Spring volcanic field split into two volcanic belts, a western and an eastern volcanic belt. What's important to know here is the western is the low silica and the eastern is the high silica. The high silica in purple are the volcanic domes that surround basin deposit. There are no volcanic domes in the basin. They just surround it, and they're part of the drainage basin divides. So if we blow up this black box that outlines B, we get to the map on the right. So the basin deposit's kind of off the east-southeast side of the eastern volcanic belt. And again, this is a simplified geologic map showing the major rock types in the area. We have basalt, the prominent basalt flow I pointed out in the picture. We have tan alluvial sedimentary rocks, mostly coarse conglomerates. And then what we're really interested in, the salmon color, which are all the lacustrine sediments. So the sedimentation in basin is ongoing throughout the time of volcanism. We have basalts that are interbedded with the sediments, with the clay stones. We have tuffs that are interbedded with the clay stones. And I just also want to point out again that we have several prominent rhyolite domes that are surrounding the basin, and that's really important for the lithium source. So just give you a taste of what these rocks look like in outcrop, first starting with the basalts, the oldest rocks. The dates here are between 14.6 and 8.4 million years as potassium-argon dates. We did not have the opportunity to do new geochronology in this area as part of the project, which is something we have proposed. Again, they're interbedded with, the basalts are interbedded with claystone and tuff throughout the basin. But most of the textures, if you start really looking at this, most of the textures of those basalts show that those basalts, when they erupted, interacted with water. And I just want to show you a few of those flavors. In picture A, that basalt lava flow in the center of the picture is interbedded with sandstone and tuff, and it has pepperitic margins, which means when it flowed into that sandstone, the sandstone was water saturated, and the sand interacted with the margins of the basalt lava flow. The basalt got exploded into the sand, and the sand got ejected into the basalt. And you can't really see the textures so much without a close-up picture, but that's a really great example of water-lava interaction at the surface. There are two pictures, B and C, of a basalt lava flow that is intensely weathered. And in one case, in C, almost actually weathered to clay. When I first stepped out there, I thought a lot of these clays came from basalt. Turns out that's not true. But they have displayed, this saprolitic type weathering is very common when basalts erupt in water. Because the water, when it reacts with the olivine and pyroxene in those flows, it will blow up the mineral structure and cause the basalt to weather really intensely. In picture C, there are two flows, one that is saprolitic and one that's not. And the upper flow is actually completely subaerial. So you can tell the difference between them for those textural reasons. Picture D is showing some evidence of explosions, basaltic tephra and scoria. And picture E and F are basalt block sags. So these only form when you have explosive volcanic eruptions, water lava interactions that break the rock apart and eject it like a cannonball into the surrounding sediment. If the sediment is wet, you'll have soft sediment deformation underneath the block. And it's hard to see in this picture on the right, but my rock hammer is right there. And that block is more than 3 meters across. So these are intense explosions. And there are many, many basalt block sags in the field area that have soft sediment deformation under them. So this is like really diagnostic evidence that's saying, okay, there was an explosive eruption and it's a wet environment. The rhyolites are really beautiful. Dome eruptions everywhere in the eastern volcanic belt initiated with a tuff ring explosion. So every single individual dome had an explosion that created a tuff. That tuff is at the base of the lava, and then afterwards, lava filled in the crater and created the dome. So a typical rhyolite dome is in picture A. Again, these are around 12 to 8.8, depending on which volcanic belt you're in. Pictures B and C, lithic lapilli tuff is really pumice-rich, has a lot of country rock in it from those explosions. Picture C is an ash tuff. This is really important, this one. The ash tuff is exposed everywhere in the drainage basin, everywhere, all over the Proterozoic rocks. You can find it in a lot of places. But where you never find it is in the basin stratigraphic log in the drill core. So the ash tuff itself is not located in the sedimentary record in basin, within this crater. And that becomes important later. Pictures D, E, and F, all pictures showing different textures of what happens when rhyolite erupts, is hot, and interacts with water. Becomes hydrated, and let's see, picture D is a feature called a lithophyse, where when you devitrify volcanic glass, you start to get crystallization of feldspars. There's a little hole in the center, and you can have really beautiful crystals of quartz or other minerals grow in there. Picture E is an Apache tear, and a piece of true obsidian surrounded by perlite, which is devitrified and hydrated glass. So that's what happens to glass when it interacts really quickly with water and it's still hot. And then picture F is spherulites, which are located everywhere in basin. Every single dome is devitrified in this way. You find these facies at every location. The claystone. Okay. There are 2 clay beds, an upper and a lower clay, and those clay beds are separated by a lithic lapilli tuff. The upper 2 pictures are showing pictures of the claystone in drill core. And I forgot to point out on the geologic map of where the drill core was, BES 2307. I hope you guys all saw that on the map. But that's some examples of the lithium-rich zones. The clay is a magnesian smectite clay. It is multicolored. It is massive to bennett in some locations. There are rare paleosol horizons with root casts. There are some carbonaceous layers where the people who log the core are saying, you know, they smell the sulfur and this really organic material. The mineralized clay is really greasy and waxy. And when you pull it out from the drill core, it's just like slop. It's super wet, it's really waxy, you can form into balls. But at the surface, it's all dried out and has that very common popcorn-like weathering texture that clays get. And then everywhere in the core, the upper and lower clays are associated with a really abundant dolomite, carbonate, and magnesite nodules. So this is pretty common for these types of volcano-sedimentary deposits, probably with the exception of the color. From what I hear of other locations, usually all the volcano-sedimentary clays are gray, and that's not the case in basin. There's another really curious deposit, and this is why a lot of people go there looking for agates to polish, and that is the volcanic sinter. This is a deposit that cross-cuts the clay, and it's composed of alternating dolomite and amorphous silica and chalcedonic agate. In some cases, it's laminated. Other places, it's massive. There are mounds, morphologic mounds of this material kind of spread all over the surface. From those mounds, you see aprons of dolomite kind of sort of extending out from those mound locations. And the really, really awesome thing that I found kind of late in the field season is picture E, which is a spring conduit. So I've interpreted this volcanic cinder deposit as hydrothermal deposits for all of these reasons. This is Alex Huff. She did her PhD, and part of her PhD in this area. She's standing on one of those mounds, which is kind of hard to distinguish from the rest of the ground surface, but it's white, and bright white, and it has an oxidized rind in some locations. And just to her left, in the right of the picture, is another mound. And in a lot of locations, there's maybe 15, 16, 20 of these mounds all located around one another with an apron of dolomite extending from it. Okay. So the stratigraphy and geologic mapping. I'm only going to show one stratigraphic column, and this was made from the drill core, from the logging of BES 2307. It's in the Bradda Head exploration area of Basin North. It's still slightly along the basin margins, but getting towards the basin center. And I want to start with the base of the column, because I know the font here is a little bit small, but I just couldn't fit it all. This core goes down to about 220 meters depth, and the deepest deposits that were cored begin with sandy claystone and carbonate and go into the lower clay. So this is interpreted as the early alluvial, but then lacustrine environment. The second interval I want you to pay attention to is this lapilli tuff, interpreted as a primary pyroclastic flow. It's zeolitized, but it is not mineralized, has almost no lithium in it whatsoever. That lithic lapilli tuff is about 15 meters thick, and then you get into the upper clay, which is the claystone that is the mineral resource for basin. And this is interpreted as a lacustrine deposit, which we'll get into the details in a second. We get to the next interval, alluvial volcaniclastic sandstone, another lithic lapilli tuff, which is baked. So the basalt that overlies it is a subaerial lava flow. It's not a subaqueous lava flow because of that baking horizon. It had to be hot. And then finally, on top of that is this volcaniclastic fan. So this is the stratigraphic package. We have claystone, clay, tuff, clay, and then transition into alluvial and subaerial environment. Okay, the other things that are on this diagram are the mineralization for lithium. So the upper clay is the ore deposit. I keep hitting the wrong button. Okay, here we go. There is a lithium-rich zone that is between 5 and 40 meters thick or so, right in the center of the upper clay, and this is where we really want to focus. That lithium-rich zone correlates with molybdenum, which is anti-correlated everywhere else. There's almost no molybdenum in the entire upper and lower clay, except for in very few locations. The lithium is correlated, or is anti-correlated to both potassium and aluminum. And this is really important for all volcano-sedimentary environments. Where you have aluminum, you're not going to get a lithium mineralized clay. It's going to take up the position in the mineral structure, and it's going to kick out lithium. So you have to have an area that is aluminum poor, and in that case, lithium can get incorporated into the clay mineral structures. The colors on this diagram I'm pretty proud of because they represent the Munsell color that was logged for every 3 meters in the core. It's the RGB values for the Munsell color. So that's the true color of the clay and all the other deposits that you see. That took me a really long time. In another column, we have a bunch of little symbols. They mostly represent the carbonate nodules that are present. The one dark, at the dark circle at the top of the upper clay is the silica related to this volcanic sinter deposit. And then we have a bunch of lines that are labeled A, B, C, D, E, F, G, and H, et cetera. Those are all the sieved horizons where Brian just painstakingly sieved the clay to look for what was the parent material in the clay, what's left over once we get rid of all the clay. And what he found was that 9 out of 10 of those sieved horizons contain only euhedral quartz and biotite. So they very likely have a volcanic ash provenance. Now we come back to the fact that the volcanic ash is missing in the stratigraphic record. We have lithic lapilli tuff, the pumice-rich tuff, but we don't have any ash tuff. The ash is completely missing, but what we do have in place of it is claystone. Okay. Next, the geology. Another simplified geologic map, just because you don't want to put the whole map up here. You guys won't be able to read it, right? But the colors here are the same. The dark purples are the high-silica rhyolates, and then we have the tan and blues, basalt, and the alluvial conglomerates. But I did split out the clay, which is all, the clay deposits are located in two main areas on the surface. One to the lower right, which is the basin east claim of Bradda head lithium. Another to the sort of central part, which is the basin west claim of Bradda head lithium. And then a third in the center that is buried underneath of that volcaniclastic fan, which is the basin north claim of Bradda head lithium. Everywhere the clay is exposed at the surface, it is part of a very complex landslide. It's nearly impossible to figure out. These things are huge. They've been activated multiple times, and they have a lot of reverse stratigraphy, a lot of overturned beds, and it's just really, really complicated stuff. But once you get into the areas where you can actually take some measurements, what you find is that the entire stratigraphic package is all dipping towards some location that is in the center of this volcaniclastic fan. They're dipping approximately 7 to 9 degrees in a kind of radial centroclinal dip, and they're all pointing towards something, the entire package. So if you start to measure the strikes and dips on the basalts, on the tuffs, on any sandstone that is exposed there, you'll find that it's all dipping towards this one central location. But what I didn't know when I was mapping this is that Bradda had gravity data, and they've so just really grateful for all the data sharing and the collaboration here. And when you overlay the gravity data, what you find is that there's a gravitational low right in the center of that volcaniclastic fan, and all of the rocks are dipping towards it. So this is really strong evidence for post-depositional subsidence over something, right? What is it? Something has to be subsiding underneath of there in order to get those radial centroclinal dips. And that's where the interpretation of the Mar crater comes in, along with all the other water lava evidence. Just to point out, because I had neglected to do so before, where the whole BES 2307 is, it's right on the, right on the border of Basin North and Basin East. So it's located right there. So that was that stratigraphic column that I just showed you. When you start to do the math, the hypothesized Mar crater is about 3.5 kilometers wide and at least 300 meters deep, although I haven't drilled to the bottom of it. And it is filled with lithium mineralized clay, a lower clay, an upper clay. It's filled with tuff and basalt. There is sparse interbedded fanglomerates coming from the crater wall margins, which is very typical of Mar craters. Because they're so steep, they'll often have mass wasting along the crater margins. So when you start to look at the drill core along the edges, you'll see these alluvial coarse conglomerates interbedded with the claystone that are kind of shedding off the crater walls. This is a cross-section of what that might look like, and correlated with 5. Let me go back 1 second. This is A to A prime, that line there. So northwest to southeast. And we have 5 drill holes in the southeast that show a really nicely dipping sedimentary package. It's very predictable, dipping towards that gravitational low. The northwest side of the diagram is interpreted, but it is interpreted based on all of the structural information we have from the surface and trying to correlate those rocks with the southeast part of the diagram. And this is just my idea here. You know, there's likely a diatreme breccia beneath the basin deposit that is subsiding and causing that radial centroclinal dip of the entire package to subside with it. And that's very common for Mar craters all over the world. Other evidence that supports this is there are no basin-bounding faults. This is not an extensional basin. There's no evidence of basin-bounding faults in this area. There's no facies that would correlate to the claystone, like thick packages of sand. There's just nothing. It's just claystone, and then it's Proterozoic bedrock. That's it. That circular gravitational low is there. We know the crater is about 300 meters deep, but the drilling has not reached the bottom. And I just want to mention there's a potential that there are multiple coalesced Mar craters in this area. There was a through-flowing drainage system at the time, and it's very possible that multiple dikes intercepted the water table and caused multiple craters. We just don't know. But I have a feeling that there might be, because this one's quite wide, and it's wider than we think. We don't really understand the morphology that much because we don't have the drill penetrations all over the field. Okay, lithium and molybdenum mineralization. This is a Google Earth image of the basin area looking northeast. Again, that A to A prime is the blue cross-section line. The dots on this diagram, every circle is assay data from a surface clay sample, and every cross is assay data from a drill core sample. And they're colored by grade. So the purple and pink colors are higher grade, and the yellow and blue colors are lower grade. This is all Bradda had data that they shared with us and were able to plot up. I have the approximate diatreme boundary plotted on here, but again, I'm really not sure of that. I just really don't understand the morphology very well. But one thing that popped out at me when I saw this data plotted like this is that all of the surface clays are depleted in lithium, and all of the drill core clays are enriched in lithium. And that to me says that there's almost certainly post-depositional mobilization of the lithium occurring, where it's concentrating as it flows, as it moves, water moves downward into the central part of the basin. The gravity contours are overlaid on top of that, showing the gravitational low, again, right here under that big alluvial volcaniclastic fan. All right, so lithium sources. Going back to the recipe that I was talking about, you need to have a source of lithium. It's probably rhyolitic magma. So I started thinking about how would the lithium be mobilized from the magma at the time of the eruptions? Is it during the eruption? Is it close soon after the eruption? Is it sometime later in the geologic record after the eruption? And so what I did was go around and collect all the different facies. So I collected the fresh lavas that are not devitrified, that haven't been altered by water. I collected the devitrified facies, I collected the tuffs, and just started kind of grabbing at everything that I could. And I did this with multiple domes. And what I found was that the unaltered high-silica rhyolite is very enriched in lithium compared to crustal levels surrounding that. The rhyolites have 143, 247 parts per million lithium. These are unaltered rhyolites. But when you look at the devitrified component of that, the partner of that, then the lithium is gone. So the devitrification process, the interaction of rhyolite with, when it's erupting, with water as it's cooling, is allowing the lithium to leave the rhyolite and be mobilized into the hydrologic system. So that process happens very soon after, soon in terms of geologic time, after the rhyolites are erupted. The other important thing here is the volcanic sinter. The volcanic sinter, which in this case is dolomite, is fairly enriched in lithium, 390 parts per million. The non-mineralized ash, and when I say that, I just mean that it hasn't been altered, this is just a primary ash, is very enriched in lithium, 222 parts per million. And then we have mineralized clay at almost 1,000 parts per million. So what is one of the sources? I think from this you can say that the devitrification process of the rhyolites is allowing lithium to leave the rhyolite and be moved into the hydrologic system and concentrated elsewhere. Another possible source, of course, is the ash itself, not just from the rhyolitic lavas, but the actual ash that is falling over basin. If you recall, it's not located in the basin stratigraphic record. There's almost no ash shards there at all. Only the remnants of ash, which these are photos of the sieved material. We have a little bit, tiny bits of pumice, a little bit maybe pyrite nodules, biotite, and quartz. So the claystone has a parent material, and that parent material is very likely volcanic ash that has been dissolved. And when it's dissolved in alkaline lake waters, it releases its lithium into that water itself. And another really important piece of diagnostic evidence for that is this picture on the right showing a lapilli tuff grading into, that's not a sharp boundary, that's a gradational boundary into claystone that is highly mineralized. The third potential source for lithium mineralization, for the lithium itself, is hydrothermal alteration. You can't ignore this because of all of the volcanic cinder deposits located in the area and particularly cross-cutting the clay. And so lithium is positively correlated with magnesium, molybdenum, arsenic, and sulfur. The charts here are showing on the top lithium versus arsenic, lithium versus potassium, lithium versus molybdenum, and then lithium versus sulfur. So the drill core BES2308 is always on the left, so the concentrations here on the left-hand side are always lithium, and then on the right-hand side, in this case, would be arsenic. This middle zone here is the high-grade lithium-rich interval, HG for high-grade. So we see where we have increases in lithium, we have increases in arsenic. Where we have increases in lithium, we have decreases in potassium. Lithium is anti-correlated with the potassium. It is correlated in some locations with molybdenum, which is, I keep mentioning that because it's a little bit curious, and Joey and I have had many conversations about where the molybdenum is coming from. And it is also correlated with sulfur, a sulfide-rich environment. So it's very possible there's been hydrothermal alteration here. The problem is we didn't do any mineralogy. We have no we don't understand well the clay species at basin. We know that it's a smectite, but we don't know what specific kind. We don't understand the zeolite mineralogy, and all of that would get us to whether or not it's been hydrothermally altered. So that's something we have in the works in a proposal. Okay. So the molybdenum anomaly. I was just at a meeting in Sacramento last week with a lot of state geologists, and we're all talking about this particular problem. Volcano-sedimentary lithium deposits and the curious aspect of molybdenum associated with them. And one of the geologists there suggested to me that I look to biological material. And I started thinking about this, and I was like, this might be actually right. So if we zoom into the stratigraphic column, we have a lithium-rich zone in the center of the upper clay. And that lithium-rich zone is correlated with molybdenum. That's here in the second column here. There are a few spikes in molybdenum through the upper clay, and then one large spike in the lower clay. And everywhere you see molybdenum, you also see in the stratigraphic record textural evidence that there may have been some sorting, say, through the water column. You have wavy bedding. Up here we have a root zone correlated with the lithium-rich zone, correlated with molybdenum. We have some planar bedding. Everywhere else, the clay is massive, right? You don't see a lot of bedding in the clay core at all, but where you do see it, you often see molybdenum. So I started reading about this and realizing that eukaryotic cells take up molybdenum in anoxic environments and in sulfide-rich environments. And they can enrich molybdenum in a sedimentary deposit to thousands of parts per million, even though the molybdenum in the water may be very small. And so it's very possible that the microorganisms and enzymes in the lake sediments themselves were taking the molybdenum into their cell structure and concentrated it at those horizons. This is just an idea. All right, so some conclusions for you guys. Basin is a volcano-sedimentary stratigraphic package that's located inside a Mar crater. It's composed of lithium mineralized clays, two claystones separated by lapilli tuffs. It's interbedded with basalts, and the whole thing is capped by a subaerial volcaniclastic fan. The lithium is almost certainly sourced from nearby hydrated volcanic rocks that are the rhyolitic domes, and that there was a lot of lithium loss that happened very soon after those domes erupted, and that lithium was concentrated through the drainage basin into the Mare crater. That Mare crater had to be a closed hydrologic system at the time that these clays, and throughout the time these clays were forming, in order to concentrate the lithium in the sediments that much. The sediments themselves likely formed from alkaline lake water, in some cases periodically anoxic, sulfide rich, and the volcanic glass that fell into that lake dissolved and precipitated out of the water column as a smectite clay. So the lithium was enriched in the lake by both the domes and the ash tufts that fell over or into the lake itself. And those sediments were very likely hydrothermally altered post-deposition, although that still needs to be worked out with a lot of clay mineralogy. Some of the origins of the clay really remain unresolved. On the left-hand side, we have the volcanic glass provenance. Like, we know that, you know, there's no ash in that clay, but the lithic lapilli tuff grades into clay. The clay has tough chips in it, has biotite in it, has quartz in it. There is an ash provenance there. What effect did diagenesis have on all of this? How was lithium incorporated into the clay mineral structures? And what mineral species are there? What was the temperature constraints? What were the geochemical constraints? All of that needs to be worked out with the clay mineralogy. We have evidence for this post-deposition hydrothermal alteration. We have these spring conduits cutting the clay. We have an agate lag. We have laminated silica and dolomite in the spring mound aprons. All of this is saying, yes, hydrothermal alteration occurred, but to what extent? Because this has been evoked in the McDermott caldera as a process for hyper-concentrating lithium to the 10,000 parts per million that McDermott has. Our next steps are a number of things. We have a pending Core Minerals proposal that hopefully will address some of this stuff. I'd really like to know to what extent the post-depositional hydrothermal alteration was responsible for the clay mineralization. In order to do that, we need mineralogy, like I said, additional drilling and assay data, and a characterization of the sinter itself. What's the aerial extent of the basin at the time of deposition? Are there multiple Mare craters? Additional mapping, whole rock geochemistry, geochronology. There are many other questions that need to be addressed there. It's really just a fascinating area that I really feel the privilege to have worked in. So with that, I'll take any questions, and thank you for your attention. Do we have a mic, or should I pass it out? Okay.
Is it on? Is it on? Go ahead.
I got the mic. What do you think is creating that grav low?
I'm sorry, what do I think is creating?
Why is the gravitational low there?
Oh, the gravitational low. That low is really the signature of the claystone versus the surrounding Proterozoic rock. So that low is essentially defining the crater rim and the crater center. The thicker the claystone, the more prominent the low.
You don't think there's a possible meta-igneous rock down there somewhere that is low density?
You might have to ask Joey that one.
And
He's sitting right in front of you.
Where's all that magnesium coming from? You got a lot of magnesium there.
We actually had this discussion in Sacramento about where's all the magnesium come from. In this particular area, and this is actually true for many volcano-sedimentary environments, basalts are there. And the basalts, like I had noted, are intensely weathered. Basalts are high magnesium rocks. So in this case for basin, that magnesium may be coming from the alteration of the basalts. It's very possible.
You don't think the magnesium is magma source?
Well, yeah, from the mafic lavas, yeah.
What kind of basalts are
Tholeiitic, the older ones are tholeiitic, the younger are alkaline.
Just one wild final comment. I've seen a lot of serpentinite pipes that have gravity low signatures like that. Do you have any borates there?
No borate here, but borate is associated, are there? No borates, that's what I thought. It is associated with many other volcano-sedimentary deposits,
Right.
borate is, yeah.
Okay.
How does the kaolin manifest itself in the area?
I'm sorry, I'm a little bit hard of hearing and there's an echo.
I'm sorry, the kaolin, you said you had some kaolin clays. Are they
Kaolin.
minor?
Kaolinite?
Yes.
Yeah, oh, minor. Yeah, it's a minor association.
Are they altered minerals?
I actually don't know. I don't know. It was an observation that was noted in an old it's a piece of gray literature that was a mineral resource assessment where they did some XRD work on the clays and showed kaolinite. So I didn't see that myself, but it was reported in literature, which is then, yeah.
So
That's
it's
it.
minor in
Yeah, very minor. Yep.
Yeah, I was just wondering if you mapped out the distribution of your center conduits. Is there any trend to them? They follow linear trends? Are they randomly oriented? What's the deal with those?
Yeah, I didn't get the chance to do that. They are the only place I found them, which is, like, I only found them in one location, the conduits. But everywhere the center is located, it is associated with some small displacement high-angle normal faults. And so almost certainly there's water moving up those structures, which are older overall, because the center does cross-cut the claystone, right? So, but I haven't mapped the conduits. There's only a few of them that I found, maybe 5 of them, 6 of them, and the one that I showed there is probably the best condition. But it is definitely something I'd like, because I didn't get to focus on those center deposits as much as I would like in order to characterize them. Yeah.
Cool, thanks.
Yeah, thanks.
Yeah, I got a question. I'm a little curious about the nature of the lithium-aluminum relationship. So you said that the lithium goes into minerals that are relatively low aluminum. And so, but where you have the lithium enriched is a clay zone, which as you progressively alter weather rocks to become more clay-rich, you remove everything else and increase aluminum. So what's going on there? Is that something that was pre-existing low aluminum rock to begin with, or were they clay altered after the fact or something like that? I guess I just don't, it's a question because I'm curious about that relationship.
Yeah, exactly. Yeah, that's a great question. So the tuffs, so let's just assume that the clays have a volcanic ash provenance. It's a rhyolitic tuff, and the aluminum concentrations are somewhere between 11 and 14% from the whole rock geochemistry. And so if that volcanic ash is dissolving in alkaline water, you would expect all of those cations to be present in that lake. So something has to be taking up the aluminum in order for the lithium to be incorporated into a magnesium smectite clay. Because otherwise the aluminum would be. The aluminum and magnesium can kind of switch places. So whether that aluminum is in the smectite clay and just a small amount of it is there, and then the lithium was able to be, because there's so much of it, perhaps that's the answer. But certainly you have to have a process which removes the aluminum, and I don't think we understand that very well about where that is going. There are only 2 mineral species that we know about, the smectite and the illite. Whether there are others, I'm not sure, which is really where I think there's a dearth of information to be learned from the clay mineralogy that we really don't understand. But yeah, it's a good question.
I think we have a question on the chat.
Yeah, well, can you hear me okay?
Yes.
Okay. I know of a basin, sorry I'm hoarse tonight. I know of a basin where there are very few analyses of rhyolite and what was identified as weathered rhyolite that showed that same high lithium, low lithium relationship. If you only had a hand lens, would it be conceivable that somebody would look at your devitrified tufts or rhyolites and call them weathered, and therefore lithium is a product of surface weathering? Is that conceivable that somebody would make that different call?
Yes, you could lose lithium through just the superficial weathering process. However, the processes that are acting on these rhyolitic magmas as they cool are integrating water throughout. And so you really can't make the argument that there's no lithium loss as the magma is devitrifying, and particularly as the obsidian is being hydrated. And this is true for not just lithium, but many mobile elements. There's another study, I think in New Mexico, that showed that tin was mobilized during devitrification and hydration of these lavas. And that's been shown to concentrate lithium and other mobile elements to great extent just through that process throughout the cooling history of the magma, or lava, I should say.
Question? Can you hear me?
Yes.
Yeah, I was curious. The San Bernardino field over in southeast Arizona has some Mars, and they also have some xenoliths in the Mars, and I think that's alkali basalt. I was wondering if in your younger basalt, or maybe the other one, if there are any deeper sourced xenoliths, either upper mantle or for some reason lower crust.
I did not recognize any I actually was in the San Bernardino volcanic field very recently, so I know exactly what you're talking about. But I didn't see any xenoliths in the basalts in the Kaiser Spring volcanic field. So yeah, just literally none. There are olivine pyroxene basalts, they are alkali basalts, but no xenoliths there.
Thank you.
Hi, thank you. Are there any parallels between this system? Can you hear me?
I think so.
Okay. Are there any parallels between this system's molybdenum enrichment and maybe some of the big high-silica rhyolites that contain large reserves of molybdenum, like out in Colorado at Climax or Henderson and things like that?
So this has been an ongoing question. Where did the molybdenum come from? Could there have been, for example, one molybdenum-rich, I think I'm answering your question, one molybdenum-rich ash that fell into this alkaline lake that then dissolved and created that stratification? The issue with the molybdenum is there's stratification throughout the basin deposit. Throughout every drill hole, it's located in the same stratigraphic layer. And it's not located anywhere else. The concentrations go down to zero everywhere else, except for in those stratigraphic horizons. And then Joey and I were just talking earlier that he had that worked up, and they can't identify any mineral that molybdenum is in. So it's curious as to why that's there. Certainly, the concentrations, when you look at the whole rock geochemistry of the rhyolites, they're tens of parts per million molybdenum. But that doesn't mean it can't be concentrated further, right, if it were dissolved and the ash was dissolved in the lake. But what is concentrating it is the question, because it hasn't been seen in the clay mineral structures itself.
Are they adsorbed onto these surfaces or something like that?
Sorry?
Are they adsorbed? Are they just surface complexes on these things?
I don't know, something to look for, really. I hope that I hope that our proposal will be funded, and then we can work up all this mineralogy and really get to look at what's happening here and where these cations are. So, yeah.
Cool, thanks.
Yeah. Well, thank you. I appreciate it. I also, I just want to, I don't think I did this, but I want to give a shout out to my team again, and also to the collaborating efforts with Bradda and Joey, was just integral in making this all happen. So thank you for that. Yeah.
Does this work? Thank you, Lisa, very much. So we reinitiated a long tradition here of giving a plaque to a rock on a pedestal to the speakers. and this rock is a olivine forsterite peridot from Peridot Mesa. And since you've been studying the mafic rocks in Arizona, it seemed appropriate.
I
All right.
appreciate that. I love this.
Okay.
Great. Thank you.
You're welcome. Thank you. Thanks to Lisa. The rocks donated by Karen Wenrick. So